Okay, so it's my pleasure to introduce our next speaker, Thomas Hulse from Boston College, who's going to talk about the non-vanishing spectrum of arithmetic progressions of squares.
Thank you so much. Thank you to the conference organizers for giving me the opportunity to speak today. Maine, Quebec has been, and Quebec-Maine, this is Quebec-Maine, excuse me, has been my favorite conference for the last 5 years. I remember last year, Stephen J. Miller expressed a sentiment to the effect of this was one of his non-negotiable weekends in terms of things that he had to attend. And I found that really resonated with me at the time. And I'm saddened that I can't be there in person, but I am happy that I have the opportunity to participate in this capacity, nevertheless. This is joint work with Chan-Young Kwon of Sun Yat-sen University, Shuhai, David Larry-Duda of ICERN, and Alexander Walker of Rutgers University. First, starting with what are arithmetic progressions of squares. So consider a primitive length 3 arithmetic progression of square integers a squared, b squared, c squared. So what we mean is the difference between c squared and b squared is the same as the difference between b squared and a squared, where all of these a, b's, and c's are natural numbers. And let's also assume that a is less than or equal to b is less than or equal to c, and that they're pairwise relatively prime. It turns out if any two of them are relatively prime, then they are all pairwise relatively prime. We observe that length 3 is the shortest length sequence for which the term arithmetic progression actually means something, because if you only have one term, then it's an arithmetic progression no matter what the term is. And if you have two, the same is true. So you need at least 3 to call something an arithmetic progression. But we also know, due to Euler, among others, that there aren't any non-trivial arithmetic progressions of squares, primitive arithmetic progressions of squares, that go beyond 3. So I'm actually just going to drop length 3 and just for brevity say primitive arithmetic progressions of squares, or if I get lazy, just arithmetic progressions. I won't be talking about any other arithmetic progressions in this talk. We have devised a way of counting the number of arithmetic progressions of integer squares given certain restrictions to the size of the integers. So since I want to start by noting that given this relationship between a, b, and c, we are able to rewrite it as integer points where a squared plus c squared is equal to 2 times b squared. And then by dividing by b squared, we are now talking about the number of rational points on a circle of radius to the square root of 2 in this sort of octant where y is greater than x is greater than 0. I should say greater than or equal to. And so there's a nice sort of geometric interpretation of this as well. With this correspondence in mind, I will state our first theorem, which is that if we fix a delta between 0 and 1, then for any epsilon greater than 0, that will be true throughout this talk, the epsilon greater than 0, the number of primitive arithmetic progressions of squares, a squared, b squared, c squared, such that the middle term squared is less than or equal to x, and the ratio of a over b squared is less than or equal to delta is 2 over pi squared arc sine square root of delta over 2 times x to the 1/2 plus this error term. This seems like a very sort of odd result in terms of asymptotics, but when you look at it geometrically, it can actually be stated as an equidistribution result, basically saying that the number of reduced rational points, a over b, c over b, on a circle with radius the square root of 2, with a certain bounded height, that is the denominator, the reduced denominator can't be above a certain value, is proportional to the angle. This seems like a very natural thing to assume, that there is not some special part of the circle that has more rational points than others. The main term of this asymptotic is not difficult to obtain using elementary methods. In fact, there's a nice treatment by Ramintaglu Begash, whose name I'm probably butchering, I apologize. And he does it for x squared plus y squared is equal to 1, but it's not hard to see how the methods transpose over to our case. However, our error term is non-trivial. We also have a bunch of other results, which I'll state more in terms of arithmetic progressions than in terms of geometry. And again, I'm just going to say arithmetic progressions and drop all of the primitive squares business, because that's sort of assumed at this point. The number of arithmetic progressions where the largest term is less than or equal to x is given by this asymptotic. The number of arithmetic progressions where the least term and the middle term are bounded by different constants is given by this particular asymptotic. And the number of arithmetic progressions where the least term and the middle term are, the product of them is bounded. So I suppose this relates to it's a little hard to describe this one. It has been described geometrically, but I sort of forget what it is given by this particular asymptotic, where the main term is actually governed by a special value of a hypergeometric function. So how do we get these? It turns out that we are able to derive these asymptotic results by studying a very particular shifted multiple Dirichlet series given here. So this sum, I don't know if you can see my mouse when I'm drawing over this. Maybe you can, good, all right, excellent. This sum is over, this R1 is basically a square indicator function. It will tell you more or less if H is a square or not. Specifically, it's the number of ways a number can be written as a square of an integer. So it's mostly 2 if H is a square and 0 otherwise, unless H is 0. So the coefficients of each sum end essentially determine whether or not hm 2m minus h is itself an arithmetic progression of primitive squares, since the difference between these pairs is equal to each other, just sort of by the way we wrote it. Oops, there we go. In particular, we are able to derive a meromorphic continuation of this triple shifted Dirichlet series to the entire C2, the complex plane squared, by means of a spectral expansion. Once we are able to get a thorough understanding of the analytic behavior of this series, we can then basically take a bunch of complicated inverse Mellin transforms to figure out what the asymptotics are. And to do this, we're going to have to take advantage of the automorphic properties of theta functions. So theta functions, let's talk about those a little bit. Let H denote the upper half plane, the part of the complex plane where the imaginary part is strictly positive. And for any natural number, let gamma naught n denote the subgroup of the integer matrices with the invertible integer matrices, such that the bottom left entry of the matrix is divisible by n. It is easy to show that these congruent subgroups act on the upper half plane via Mobius maps. This is something that is often taught in a lot of undergraduate complex analysis courses. And so suppose that we pick a particular point in the upper half plane. We are actually able to define this particular function, theta z, which is just e to the 2 pi I n squared z. And what that means is the Fourier coefficients are essentially just telling you whether or not the number n is a square. So again, we have our square indicator function that we saw a few slides back. This series is uniformly convergent on compact subsets of the upper half plane. What's more, it has this sort of automorphic property. If I take a matrix element of gamma naught 4, then theta of gamma z is equivalent to a weight factor that is pretty straightforward to understand times theta z. And this is another way of saying that theta of z is a weight 1/2 holomorphic form of gamma naught 4. And you can prove this using the Poisson summation formula on the generators of gamma naught 4. We also can show, basically by taking advantage of the known properties of theta z, that theta of 2z is also a holomorphic form of gamma naught 8, but it has of gamma naught 8 as opposed to gamma naught 4. You need to expand. You need a slightly smaller group, and it also will have a Nebin typus. That is to say, in addition to this weight factor, you're going to have a chi-d that's sort of inserted there next to it. We want to observe first that we can define a function v of z, which is given by y to the 1/2 theta 2z times the conjugate of theta z, is a weightless automorphic function on gamma naught 8, which is to say the upper half plane modded out by gamma naught 8 with Nebin typus chi. That is, if we take an element of the upper half plane and we act on it by a matrix in gamma naught 8, then v is almost unchanged save for this Nebin typus. Furthermore, let's define an inner product on this space, which we can do. It's basically we just integrate two automorphic forms against each other over the fundamental domain of H modded out by the action of the group. This is the Peterson inner product. And when we talk about functions that have this sort of automorphic property that v of z has and are also square integrable, we define that to be the L2 space of these particular forms. Unfortunately, while v of z is an automorphic, I say L function, that's a mistake. It should just say automorphic function of gamma naught 8 and character chi, it is not yet square integrable. We're going to have to do something to it to make it square integrable. And the reason we want to do that is because square integrable functions have other nice properties that we want to exploit. So consider a Poincaré series that is given by basically averaging over the imaginary part times an additive character with a particular chi. This is the level 8 twisted Poincaré series. We would like to be able to take the inner product of this Poincaré series against our V previously defined. And by unfolding using the Rankin-Selberg unfolding method, we are able to actually get our, there's some mistakes here. This should be gamma of S and this should be S, but morally this is the right thing. This series is the series we're trying to get, and we can get at it exactly by considering these inner products and then summing over H. And from there, we would wish to take a spectral expansion of the Poincaré series and rewrite the left-hand side of the above equation as a sum of eigenfunctions of the Laplacian, and then obtain a meromorphic continuation of the series on the right. And that is our strategy. Unfortunately, as I said before, V of Z is not square integrable. And so we need to regularize V of Z by subtracting off a main term that causes it to grow too much at cusps. Now, gamma naught 8 has 4 cusps, infinity, 0, 1/2, and 1/4. And it turns out that our V of Z only has polynomial growth at infinity and 0. So we let EZ S chi denote the weight 0 level 8 Eisenstein series with the same character that we've been seeing throughout this talk. This is a lot like our Poincaré series. It just doesn't have the additive twist attached to it. Maybe it's better to say the Poincaré series is a lot like our Eisenstein series. And it turns out that special value of this Eisenstein series, EZ 1/2 chi, has only polynomial growth at infinity and 0. And in fact, that polynomial growth exactly cancels the polynomial growth of y to the 1/2 theta 2z theta bar. And as such, if we take the difference between these two objects, we get an automorphic function that is in fact square integrable. And because it's square integrable, we are now able to take a spectral decomposition. So what's interesting about this spectral decomposition? So first we should talk about what a spectral decomposition actually is. If I have a function that is square integrable, we can write it as a linear combination of Moss forms, where the coefficients are given by the Peterson inner product of the original function against those Moss forms, plus a sum of integrals against Eisenstein series. Eisenstein series are like the ones we saw in the previous slides with some tweaks. These Moss forms are automorphic forms. They are not generally holomorphic. They have, for this particular weight and level, they have k Bessel functions instead of e to the 2 pi iz in their Fourier expansions. They are eigenfunctions of the Laplacian on the upper half plane modded out by gamma naught 8 with a character. And so this is a general result. In Philippe Michel's work, you can find this citation, and this is basically the bread and butter for me and a lot of my collaborators for getting at a lot of these shifted sums, is exploring these spectral expansions. Now, since the Eisenstein series on gamma naught 8 has only 2 singular cusps, 0 and infinity, the continuous spectrum that we saw in the previous slide for our V tilde of Z, our regularized V, vanishes since we've subtracted off the constant term, and that is exactly what the Eisenstein series are going to pick off. So we don't have to worry about the continuous spectrum in this particular example. So the continuous part of the spectrum appears to vanish. And we also have that the Eisenstein series is orthogonal to all of these Moss forms. So when we look at the spectral expansion of our V tilde of Z, the only part that survives is the part that contributes from our original V of Z, the part that, you know, wasn't an L2, integrated against these Moss forms. And it turns out that we can actually explicitly compute this, because we can let theta of Z, for example, be the residue of an Eisenstein series of weight 1/2, and then do our unfolding and then compute. This, however, got us into trouble. A year ago, when we first tried to compute these things, we thought that all of these inner products should be 0. And in fact, this is a sequel talk to a talk I gave last year at Maine, Quebec. And it was Maine, Quebec, because last year it was Maine, and this year it's in Quebec, titled The Impossible Vanishing Spectrum, because we knew something was wrong and we couldn't figure out what it was. And at the time, we weren't able to articulate the problem in a way that people could explain to us, you know, what we were doing incorrectly. And the reason we thought that these inner products vanished is because it turns out that they had as a factor the residue of the symmetric square L functions of these Moss forms. And most of the citations that we could find on symmetric square L functions of Moss forms is that they're entire. And so this residue should be 0 because there isn't a pole at s equals 1. And the more we sort of dissected this thing, we needed a Moss form that had real coefficients, but still had this non-trivial Nepen typus, which meant that every Fourier coefficient on a prime, where the character was -1 should vanish, which seemed to contradict the Sato-Tate conjecture. And so we were really confused as to why this thing should ever not be 0. And it turns out that we weren't considering a subset of Moss forms that are very well understood, but not usually paid a lot of attention is often paid to them in the construction of these spectral expansions, because they're sort of treated like everything else, which is dihedral Moss forms. It turns out that dihedral Moss forms, which are Moss forms that arise from Hecke characters, that is, their L functions are exactly the L functions of the Hecke characters, are exactly characterized as those L functions of Moss form, are exactly characterized as those Moss forms whose symmetric square L functions do in fact have a pole at s equals 1. And what's wonderful about this is that dihedral Moss forms, at least for gamma naught 8 with character chi, are actually very easy to completely characterize. And as such, unlike other spectral expansion results that we have gotten using similar methods, we are actually able to get extremely explicit expansions of our series here. So again, a reminder of what our series actually is, this DSW. We can write it as a sum, and this is our spectral expansion, but decoded so that we have actually opened up the Moss forms that correspond to these Hecke characters. And so, most of the terms in this are pretty understandable. The one part that we want to emphasize is here we have the L function of a Hecke character, where what's really nice about the space of Hecke characters that we're worried about is that they're all generated by a particular Hecke character, and we can just take powers of those things. And this is actually the first time we've computed a spectral expansion where we're able to actually set this thing up in Sage and verify that it works. And so, I'm pleased as punch that we were able to finally get this through. We have this spectral expansion, and now that we have it, we are able to do inverse Mellin transforms of it. And at this point, I'm getting a little more out of my depth because my contribution to this project was more on the side of coming up with a spectral expansion, where others had more to do with the actual asymptotic results. But I do want to comment a little bit about how knowing the explicit L functions does improve our results marginally here. So in particular, we use for the main results that we had at the beginning of the talk, our theorems 1 through 4, the convexity bound for these Hecke L functions, specifically that in vertical strips, we have that the L function has polynomial growth with these exponents 1/4 plus epsilon. If we assume that we have a subconvexity result, whereas we can improve 1/4 plus epsilon to some smaller value, and the Lindelof hypothesis is that these alphas can be taken as small as 0. I probably should have said alpha plus epsilon, but it's not, it's morally similar. We are able to, we get our 3/8 result from the convexity bound, but if we replace it with these alpha, we can actually get a more general result that will improve as the convexity result improves. So we're able to say that our arithmetic progressions of squares is actually the error term that we have is dependent on progress towards the Lindelof hypothesis, which is very interesting to me. Now, the amount of improvement that can be made is very marginal. What we have, the best known results currently due to, I believe, is it Wuhan, or I might be screwing that up, is 0.36859, and under the Lindelof hypothesis, it would just be 1/3, so it's a very, very small difference, but the difference is there, and I find that endlessly amusing. Last thing I want to say before I wrap up, we do also want to consider other sums that are related to this, where instead of saying 2m minus h, we might have a different constant here, and we might we have different values of h and not necessarily sum over the h's. And the reason we might care about this, for example, is that if I let this t be 5 and I sum over oh, this H, yeah, and I let H be 4. I should have just written 4 in the sum there. This actually corresponds to the Dirichlet series for the Fibonacci sequence. And so we're actually interested in studying how some of these shifted sums of square integrator functions say something about second order recurrence relations. And that's sort of a project that we are certainly percolating on right now. But I think that's a good place to stop. So thank you all again for listening to me. And thank you again for organizing this conference.
Thank you very much.